Section 10.8, Taylor series. For Taylor polynomials centered at x equals a, what if we let the degree of the Taylor polynomial, capital N, tend to infinity? So if we write out our nth degree Taylor polynomial for a function f at x equals a, either in its expanded form or in its summation form, and then take the limit as n goes to infinity, then we just have the limit as n goes to infinity of this familiar expansion or this familiar summation. And notice that this goes from a finite series to an infinite series. And also this infinite series that we have is actually a power series for the function f centered at x equals a. We can see the center of the series here and the coefficients of the series here. The coefficients c sub n are just the nth derivative of f evaluated at a over n factorial, and these are called the Taylor coefficients. This series is called a Taylor series for f centered at x equals a. And of course, we still call this a Maclaurin series when a happens to be 0. One way to generate a Taylor series is to compute it from scratch, just as we did when we were computing the nth degree Taylor polynomial. So for example, if we take the function f of x equals cosine x and a equals 0, and if we wanted to compute the Taylor series for this function at a equals 0, then we would just prepare by having the function, its first derivative, second derivative, third derivative, fourth derivative, and so on, and we would evaluate each of these quantities at the intended a value. So f of 0 is cosine of 0, so we get a 1. F prime of 0 is minus sine of 0, so we get a 0. F double prime of 0 is a minus 1. F triple prime of 0 is a 0. And we just keep on computing as many of these as we need in order to generate a pattern. Now in this particular case, since we're cycling through sines and cosines and their negatives, we eventually reach a pattern to where each of these numbers starts to repeat. And so if we were to write out the Taylor series, just think of a long Taylor polynomial. However, it's very, very important that this does not truncate after any finite number of terms n, but keeps going on forever. But it still feels familiar to what we did when we were doing Taylor polynomials. We take cosine x. We know that the general form of any Taylor polynomial or Taylor series now will be f at a plus f prime at a times x minus a plus f double prime at a over 2 factorial times x minus a squared plus f triple prime at a over 3 factorial times x minus a quantity to the third, and so on. This is very important that in a Taylor series you do not truncate this after a finite number of terms. That's the main contrast between the last section and this section. Now, since we've computed these we've computed these numbers for the derivatives evaluated at a, and from that we can generate the coefficients by dividing by the appropriate factorial, we see that for the cosine function, this comes out to be this. And since we have a pattern here, you could leave this in expanded form, that's totally fine, but we also want to be able to write it in a compact summation form whenever possible. And if you stare at this for just a little bit, you can rewrite this expansion into this summation, and this is the Maclaurin series or the Taylor series for f of x at a equals 0. You could just say Maclaurin series since it already has an a of 0. You could do this exact same process. I won't show all of the details here, but this same exact process of manufacturing the Taylor series from scratch by just calculating the function and successively higher derivatives and evaluating those derivatives at the a value and writing out the expansion and generating the pattern so that you can write it in its summation form. And you could do this exact same thing for the sine function, and when you do that you get this. And if you look at that pattern for a little bit, you see that it can be rewritten like this. And this is the Maclaurin series for the sine function, or the Taylor series for the sine function at a equals 0. One thing to note and to help you remember, you may remember from trigonometry that cosine was an even function, and you can notice that all of its powers in its power series are even powers. And you notice the sine function was an odd function, and all of its powers are odd numbers. And notice that the power and the denominator with the factorial, those numbers always match. In sine, they just happens to be odd, and in cosine, they just happen to be even. They do alternate signs, so you have a minus 1 to the n plus 1. It starts positive and then it alternates, the non-zero terms alternate sign from there. You could do the same process for the function f of x equals e to the x at a equals 0. This one's easier to compute, of course, because the derivative of e to the x is just e to the x. And I don't show the details here, but you could do the exact same thing. The expanded form of the Taylor series is just like the pattern that occurred in the Taylor polynomial. And here we're doing the same thing in the summation form. We can rewrite it like this. And so this is the Maclaurin series for e to the x. Now, in example 2, we'll look at, just like with Taylor polynomials, we can also generate new Taylor series from known ones without calculating from scratch. And this is very important. Up here above, even though I didn't show all of the details for all 3 examples, I showed it for the cosine example, you can manually compute the Taylor series by just computing enough derivatives and evaluating them at your point of interest, your a value. That is one way to calculate a Taylor series. But also another very efficient way to calculate a Taylor series is that if you have been given a function to find the Taylor series for, and it's related to a function that you already know its Taylor series, you can usually do some algebraic manipulation or some substitutions to quickly find the Taylor series for the new function. So let's look at a concrete example. We know that the Taylor series for e to the x, the Taylor series about a equals 0, or the Maclaurin series, looks like this. And I'll write it out in its expanded form as well as its summation form. And so if we want to find the Taylor series for, say, the function e to the minus x squared, which is still doable from scratch, but would require some much more involved and complicated derivative calculations. But instead of that, we could just use this as a template, and we could say, well, this function is just this function evaluated with the x being a negative x squared. So I'll take this template, and wherever I see an x, I'll put a negative x squared. So x becomes a negative x squared, x becomes a negative x squared, it's still squared, x becomes a negative x squared, but it's still cubed, and so on. And if you do this in its expanded form, and then you simplify the result, here you can see that you get a 1 minus an x squared plus an x to the 4th over 4 factorial minus an x to the 6th over 3 factorial plus an x to the 8th over 4 factorial, and so on. And so here we've written it in its expanded form. But notice you could have done the substitution here in its compact summation form, and just wherever you see an x, you put a negative x squared, and then you simplify this. And some students are more comfortable doing this. Some students are more comfortable doing this. Eventually, after you do enough of these, you'll start to become more comfortable working with the summation form, and just going directly to here is the most likely outcome of this. But notice we could just go to the e to the x template. Where you see an x, put a negative x squared. Simplify this. Notice if you split this, this is a minus 1 to the n times an x to the 2n. And notice this is the summation form for the series that you've already found. So we want you to be comfortable doing these both ways. But notice how quick and efficient that was compared to manually calculating the terms in the Taylor series and hoping to find a pattern. So I encourage you to try it this way whenever you have a function that is related to a function for which you know the Taylor series. Let's look at another example. Let's find the Maclaurin series for the function f of x equals x cubed over 1 plus x. Well, this function is somewhat familiar because if we think of the standard geometric series, 1 over 1 minus x has this as its infinite series. Notice that this is its Taylor series. And now we want to adjust this. We see 2 adjustments that we need to make. One is in the numerator with multiplying by an x cubed, and one is in the denominator by replacing this x. We want this to be a plus x, so we'll rewrite 1 plus x as 1 over 1 minus a minus x, because we have to follow this template. And now this function is the same as this, and now looking at this template, it just means wherever we see an x up here, we will replace it with a minus x. And I'll work here in the summation form just for space considerations. So I'm looking at this, and wherever I have an x, I want to put a negative x. And so now I have a negative x quantity to the n, which if I separate this is a minus 1 to the n times x to the n. and we've just found the Taylor series or the Maclaurin series for this function. We have one more adjustment to make. We need to multiply through by x cubed. So let's take this, multiply by x cubed, so we get the function that we want. I'm taking this series representation, multiplying by x cubed. Now I'll just push this to the inside of the sum. This is an x to the third and an x to the n, so this becomes an x to the n plus 3. And you could stop here for the compact summation form, or you could write out the pattern, and this is what you would get. And so this would be the Maclaurin series for the function 1 over 1 plus x. Another trick that we have in our bag is, since power series can be differentiated and integrated term by term, and Taylor series is just a special case of a power series, we can leverage that to compute more complicated objects. So for example, let's use an appropriate Taylor series to help compute the integral from 0 to 1 of e to the square root of x dx. Now at first sight, this looks like a complicated integral, and if you think back to all of the integration techniques that you've learned before, you may look at that and say, well, I can't integrate that with a u substitution. What else might I try? Now it turns out that this integral is doable with a u substitution followed by an integration by parts, but nevertheless that would become somewhat involved. And there are other integrals that you could use this technique on that wouldn't be computable by any other means. But even though we could compute this by some other complicated means, let's show how we could find the value of this integral using Taylor series. Well, since this is related to the e to the x function, let's think of the Taylor series expansion or the Maclaurin series expansion for e to the x about a equals 0. So this is the familiar form. Now we want to look at e to the square root of x. So wherever we see an x, we'll put an x to the 1/2 or square root of x in all of these places for x. And if you do that and then simplify this algebraically with the powers here, this just becomes an x to the 1/2 quantity squared, so an x to the first, this is an x to the 3/2, this is an x squared, and so on. You get this Maclaurin series representation for the function e to the square root of x. Okay, but we want the integral of that, so what we'll do is we'll take this, we will integrate both sides from 0 to 1. Remember, since this is a power series, you can integrate the power series. And when you integrate it, you just integrate term by term. So you go along to each term, you apply the power rule to each term. Notice that here, I do have this factorial in the denominator, but that just keeps hanging around the factorial. So this would be an x, this would be an x to the add 1 to the power and divide by the new power. Don't forget your factorial. Add 1 to the power, divide by your factorial. Add 1 to the power, divide by your new power. Don't forget your factorial. Add 1 to your power, divide by your new power. Don't forget your factorial, and so on. So this is our antiderivative. We want to evaluate it in itself is an infinite power series. So now we evaluate this between 0 and 1. When we plug a 1 in for x, we just get this. When we plug a 0 in for x, since all of these have x's, then this is just a big 0. So there's really no need to have anything here. And now this is a numerical infinite series representation for the value of this integral. Now here I did this in the expanded form just to diversify the different ways that we could do this problem, and also to help get us comfortable working with the summation form. Let's take this from the top and just do this in the summation form. Of course, you do not have to do both of these. I just want you to see them side by side to see that you'll get the same answers, and to see how the work looks a little bit different when you're working with the expanded form versus the summation form. So taking it from the top, what if we have e to the x is this summation form? So e to the square root of x, we would take this same template, and wherever we have an x, we would put a square root of x. Square root of x is x to the 1/2 power. So when this simplifies, we get x to the n over 2. Everything else stays the same. If we integrate both sides of this from 0 to 1, we get this. Now here's the place where, since we're allowed to integrate term by term, that means I can swap the order of this summation and this integration, basically pushing the integration inside the sum. Now I'm going to work on integrating just this with respect to x. Notice that this doesn't have an x in it, the n factorial, so I can pull this out of the integral if I like. and then just integrating this power function, we add 1 to the power, divide by our new power, evaluate from 0 to 1. When we do that, still keeping our 1 over n factorial, wherever we see an x, we put a 1, minus wherever we see an x, we put a 0. Notice that when the algebra dust settles here, that this is just a 1 to the n plus 2 plus n over 2 plus 1 power, minus this is just a big 0. And then when you simplify this, n over 2 plus 1 is the same as n over 2 plus 2 over 2. So that's n plus 2 all over 2. It's in the denominator, so that gives us a 2 over n plus 2. We still have the n factorial in the denominator. So this is our compact summation form for the infinite series that we had above here. And so notice, if you were to expand this, you would get the same series that we had above. So this is just showing you that you can get that same series representation in 2 totally separate forms. Now either way, we can conclude that the value of this integral is equal to this sum, is equal to this numerical series expansion. Now we know that this integral, normally you would say, does this series, numerical series, does it converge or diverge? But this is a proper integral, so this must be a finite number. And if you wanted to put this to the test, but if you acted like you didn't know that, and you wanted to put this to the test, you could perform, say, the ratio test on this, and you would see that this converges. And also, it turns out, you can check by looking at the sequence of partial sums, that the series turns out to sum to 2. As a last topic in this, we want to look at how complex numbers and Euler's formula, we can shed some light on these topics using power series. So notice if z is a complex number, so z is equal to a plus bi, where I is the square root of minus 1, then e to the z can be rewritten as the sum from n equals 0 to infinity of z to the n over n factorial. This is exactly what we did before, but we had an x before. Same thing for sine, same thing for cosine. So these are just our standard power series relationships, but we're allowed to apply them for complex z's instead of real x's. And the real power of this is that these power series unlock an amazing relationship. If you were to do e to the iz, where I is the square root of minus 1, this just means put an iz wherever you see a z. You expand this out. And now if you remember the way powers of the imaginary unit I go, I is the square root of minus 1, so I squared is minus 1. I cubed is just I times I squared, so it's minus I to the 4th is just I squared times I squared, so it's 1. I to the 5th is I to the 4th times I to the 1. But I to the 4th is 1, so this just gives me I. And we can keep calculating higher powers of I here very simply, and they rotate through this pattern. So when we use this, and we plug in what we get for our powers of I up here, we had this. We rewrite this as an I squared, which is minus 1, an I cubed, which is a minus I, an I to the 4th, which is 1, and we get this expansion. Now, if you were to gather up all the terms here and segregate them according to the ones that do not have an I in them, plus the ones that do have an I in them, and you may need to write out a few more of these terms to see the pattern, and you were to group the ones that do have an I together and factor out the I, you would get this as the series that doesn't have I's in it, and you would get this as the part that does have I's in it after you factor the I out. And it turns out that this is the cosine z series, and this is the sine z series. So what that tells us is that e to the iz is equal to cosine z plus I times the sine of z. And this is known as Euler's formula, a very powerful formula that's used in many branches of mathematics. And so as a quick final example, we can use Euler's formula to compute e to complex powers. For example, e to the I pi over 3. Well, e to the iz for any z is cosine z plus I sine z. My z here is pi over 3, so I put this into the cosine function. Put this into the sine function. Cosine of pi over 3 is 1/2. Sine of pi over 3 is square root of 3 over 2. And we very quickly are able to calculate this rather complicated object. It's e to a complex power, e to an imaginary power. Similarly, e to the minus pi I is cosine minus pi plus I sine minus pi, using Euler's formula. Cosine of minus pi is minus 1. Sine of minus pi is 0. and we very quickly have calculated e to this complex power.